Hello and welcome to Easy Maths. This is the first lesson on a series of lessons on the topic of quadratic equations and expressions in Form 3. It's also the first lesson on a series of lessons I want to do on all the topics in Form 3, so you can check out for them in following weeks and months. In today's lesson, we're going to look at factorization of quadratic expressions, whilst in other lessons we're going to look at completing square, solution by completing square, and quadratic formula. Again, also graphs of quadratic equations. Please like my tutorial, share, and subscribe. Hopefully it's going to be of help to someone. And so let's begin with the factorization of quadratic expressions. As we start, I'm going to say that much as at this point the concept of factorization is already introduced, or students are supposed to be aware of that, we're going to look at a lot more about the concept of perfect squares, which was also mentioned in previous lessons. And so we're going to take a lot more emphasis on these perfect squares, because also it's like half of the topic is really about perfect squares. And so let's begin by, first of all, refreshing some concept of factorization. If you're given an expression 3x squared plus 17x plus 10 and you're taught to factorize, we progress as follows. First of all, identify the sum, which is in our case 17, and this is a coefficient of the middle term. In our case it was positive, so I've just written 17, so 17 just means positive 17. If this was negative, I would have introduced a negative sign here. Again, we identify the product, which is in our case it's 30, and this is the product of the coefficients of the first and third terms of the expression that was given. Again, if this is negative or this one is negative, it means the product will be negative also. If both of them have the same signs, we have positive 30, so we don't ignore negatives. Now, we are supposed to get all the factors of the product, that is 30, in pairs. That is to mean we have pairs of numbers which, when you multiply both of them, you get 30. We're going to list all of them and then ask ourselves which ones in that pair add to the sum. Our sum was 17. So we have 1 times 30, 2 times 15, 3 times 10, 5 times 6. All of these ones multiplied together would give us 30. And these are the only pairs there are. So the question is, which of these pairs add up to 17? Obviously, it's this 2 plus 15 gives us 17. And therefore, this expression is going to be transformed to this one here by splitting the middle term 17x to 2 terms, that is 2x and 15x. Remember, we have not changed anything since 2x plus 15x is the same as 17x. The reason we split the middle term is so that we will be able to factorize in pairs. We have the first 2 terms factorized in some way and the others also in some other way. Now, for the first 2 terms, the common factor here is an x, and for the 2 others, the common factor is 5. And so we get x outside and get 3x plus 2, and again here we get 5, and then we have 3x plus 2. A very, very important part of this operation is that these 2 brackets must be identical if we are doing the right thing. If they are not identical, then we are wrong. So ensure that 3x plus 2 appears twice. And having gotten to that point, now we just write the last answer, which is going to be x plus 5. That's the first bracket. The other bracket will be 3x plus 2. The x plus 5 is this x, this sign plus, and that 5 there. So that gives us the first bracket, x plus 5. And then the 2 identical brackets happens to be the other bracket. That is the 3x plus 2. And that's the answer for the operation. That is factorizing 3x squared plus 17x plus 10. As we move on, we are going to try some more other examples, and I've listed 8 questions. We factorize these ones. Please, following this process here, you can slow the video and you factorize them. And the first 4 questions, the answers are like this. And the next 4 questions, the answers are like this, and they are very different. These form a certain category that is very different from the second half. The first half there is what we call perfect squares. And the distinguishing feature is that we have x plus 3 in one bracket and the same thing on the other bracket. We have x minus 4 on one bracket, we have x minus 4 again on the other bracket. We have 2x plus minus 3, the same thing. 3x minus 2, 3x minus 1, the same thing there. And that is very different from what we have in the second half. This bracket is not like the other one. This bracket here is different from the other one also. This is different from the other, and also that way. That means something. Whenever we factorize expressions and you get two brackets that are identical, then that expression we are operating is a perfect square. I should also say that the x plus 3 times itself can be written like this. That means x minus 4 can also be written like x minus 4 squared. That's this second answer, and the third, and also the fourth. Remember, the second half of the questions, there is no way you can write it this particular way. And therefore, just trying to emphasize the concept of perfect squares. They are the sort of expressions which, when we simplify or when we factorize, we get two brackets that are identical, and so we can write them this particular way. Now, obviously, these are the ones there's nothing we can do to write them with this particular way because the two brackets are different. Let's move on. Let me say this part, which is it's called the algebraic identity of a perfect square. The first one, we have a plus b within brackets squared is the same as a squared plus 2ab plus b squared. And if it was negative here, that is a minus b bracket squared, it will be the same way as what you got earlier there, only that the sign is negative. And so please notice that when we have a plus b, that's we have a plus sign there, the middle sign will be positive here. And also if it's negative, we have negative here. So this gives us the so-called perfect square, the identity of perfect square. And I should say that this is just a normal square. I think the word perfect in the word perfect here really means just a normal square. Since we have a plus b, if a and b were numbers, this is just squaring the numbers, only that this time around a and b are unknowns. So please get that. I have some four properties I want to explain further about the identity. And so let me see the first one. In all perfect squares, when you're working with perfect squares, expressions which are perfect squares, the first and last terms, that is if the expression is written in standard form of quadratic expressions, like this one, the first and last terms are normally squares, and they are also positive. So it's like I'm saying four things in that one sentence. We have the first term, it must be positive and a square. The last term must be square and also positive, without which it's not a perfect square. Like in this case, the answers we have, that is the right hand side of these two equations, the a squared and b squared are both positive and they are squares. And this is not negative here. We don't have a negative here. That's what I'm actually trying to say. The same case also for the second case there. A squared plus ab plus b squared. They are both, the first and last terms are positive and they are squares. Anyway, all squares should be positive. The next thing is the second term. In these two expressions here and also in these others, the second term normally is the same as 2 times the square root of the product of the first and the last. So if you take x squared times 9, find the square root, divide and multiply by 2, you get 6. The same thing as this 8. Please at this point ignore the negative. So we have x squared times 16, that's 16x squared. Square root of that would be 4x times 2, you get this. The same thing for 12 and 6. These other cases it's not possible since they are not perfect squares. The third property is that the third term, in all of these cases, the third term is normally equal to middle term divided by 2 squared. And that is only true when the coefficient of the first term is 1. That means in the first two cases here we had earlier here, since the coefficient of the first term is 1, then the third term, that is this 9, is the same as 6 divided by 2 squared. 16 is also negative 8 divided by 2 squared. So that's true for all times when the coefficient of the first term is 1. But when it's not 1, you can always make it 1 by dividing, like in the third case here, divide everything by 4, or this one divide everything by 9, and the property will still hold. The fourth characteristic I need to mention is that the middle signs are the same. Well, let me define what I mean by middle. We have x squared plus 6x plus 9 is equal to x plus 3 squared, and that's what you did the first question there. What I mean is this: the middle signs, this sign of the middle term and the sign between the x and the 3 must be the same. These are perfect squares. And the whole reason I'm talking about all of these things is so that we use this kind of concepts to operate questions in the next subtopics. Now, if we take, say, this other one, 4x squared minus 12x plus 9, this one, it factorizes to 2x plus minus 3 and a squared. Again, please notice that the middle sign is the same. Please understand that middle means just middle, that means the sign of the middle term, and in this other side it means the sign between the two terms that are within the brackets. And so having they say that, I think I'm done with the first lesson. Please check out the next lesson, which will be about completing square, and we're going to take the concept of perfect square all the more further. So thank you.